chocolate all over my face.
Okay, so what I want to talk about now is something called cardiac output. And cardiac output is the volume of blood ejected from each ventricle per minute. So the volume of blood ejected out of the right ventricle per minute and the volume of blood ejected out of the left ventricle per minute. And the equation for this is heart rate times stroke volume. So this definition should sound pretty familiar because stroke volume is the volume of blood ejected from each ventricle per heartbeat. So you take that value and you multiply it by the number of the times the heartbeats per minute, and that gives you the amount of blood going out of each ventricle per minute. The average adult cardiac output is 5.25 liters per minute. What does that mean to you guys? 5.25 liters per minute. But I mean, what does that mean functionally? It means that 5.25 liters per blood each minute is going through the pulmonary circulation. It also means that 5.25 liters of blood per minute is going through the systemic circulation. So those are important values to know. Does the body regulate cardiac output? Is it always 5.25 liters per minute? No, so the body does regulate it. When might we want to change cardiac output? When would we want our cardiac output to go up?
You're running away from a bear.
You're running away from a bear, the fight or flight response. Anybody know why you want your cardiac output? Why? I mean, yeah, sure, so more blood is going through the system. Why do we need that when we'll say, during a period of exercise, running from a bear or on a treadmill or something like that? What is it that increased blood flow is necessary for? The cells are working harder. The skeletal muscle cells are working harder. Cellular respiration. So they need more oxygen. What are the cells producing more of? What byproduct are they producing more of? CO2. So we need to get that CO2 up to the lungs in a more rapid fashion. We need to get glucose to the cells. We have to pick up and deliver things at an expedited rate. Now, how can we change that? How can we? When does cardiac output go down? When you're sleeping or resting and digesting. Yeah. How can we change cardiac output? What could we do to increase cardiac output, we'll say? There's two variables to work with here. We can increase heart rate. If we increase heart rate, then we increase cardiac output. And what's the other way we can do it? Increase the amount of blood that's going out of the heart with each minute. And does anybody know how we do that? I mean, the heart rate goes up, but what else can we do to squeeze more blood out of there?
Squeeze harder?
Yeah. Strengthen the muscle of your heart rate.
Actually, it's squeeze harder. So it causes those ventricular cells to contract more forcefully.
Right.
And that pumps more blood out.
How do you get your heart to squeeze harder?
You think about it really hard.
Well, those are two good points. Do we have conscious control over that kind of stuff? No. And what do you think is going to regulate that? What changes heart rate? What's responsible for increasing heart rate?
Exercise?
I mean, directly, it increases as a result of exercise, but what's going to actually command the heart to beat faster?
The SB node?
The nervous system. So the SA node is doing its own thing, but the nervous system is going to manipulate this and change it if it wants to. What branch of the nervous system is responsible for innervating cardiac muscle, the autonomic nervous system. And the autonomic nervous system is going to be responsible for not only increasing heart rate, but causing the ventricles to contract more forcefully as well. Normal adult blood volume is about 5 liters. So what that means is that the entire blood supply, if you follow one red blood cell, it's going to go through the pulmonary circuit and so there's 5 liters of blood total in the human body, and that 5 liters is sent through both the pulmonary and the systemic circuits each minute. That makes sense.
So if your output is 5 liters.
Not going to make sense. This is interesting here. Total blood flow at rest. So this is during a period of rest, like you guys are doing now, and normal cardiac output during that period of rest is about 5.8 liters per minute, or 5,800 milliliters per minute. And what this shows is the distribution where all those 5,800 milliliters are located. So where's the majority? What single organ has the majority of blood going to it when you're resting? The abdomen. You're resting and digesting, so most of that blood is going to the abdomen. Where else are we going? Skeletal muscles. A lot of going to the kidneys. And that's you guys are resting, and so one of the maintenance functions you do when you rest is you filter a lot of blood through the kidneys and get rid of waste products through the urine. And then this is cardiac output during strenuous exercise, 17.5 liters per minute. So about 3 times as much blood is being pumped out of the heart each minute when you're exercising strenuously. So what I want you guys to do is look at this and tell me what happens. Look at the distribution of blood of these 17,500 milliliters, and tell me what strikes you about that period of exercise, going from resting to exercising, where that blood distribution is going.
maybe like if it was kept a scale, it would probably
Yeah, it's because you've got 12,500 in there
Yeah,
and it's too
that's
big. You can't really read. Yeah, but if you look at it, oh, it's not. We'll get that.
Okay. Sydney. You want to give me one place where blood flow, really changes, and maybe talk about why?
Yeah, there's increased blood flow in the skeletal muscles.
All right. So the skeletal muscles at rest, we have 1,200 milliliters going to it. And what's going on during exercise? Increases about 10 times. And why would that be the case?
You increase a lot more energy to have muscular contraction.
Yeah, just like we talked about, those skeletal muscle cells demand more oxygen, they demand more glucose. They need to get rid of CO2 more quickly. And so you need a lot more blood going there to deliver that. Marianne, what's another place that blood flow is changing?
The skin went up to 1900 from 500.
Okay, the skin. So the skin is going from 500 to 1900. What's going on with that?
You're exercising, you sweat. You need more.
Yeah, so if you're exercising, your body temperature goes up because cellular respiration, a byproduct of that is heat, and that's increasing. So you're generating more heat, and skeletal muscle contraction creates heat. You need to get rid of that body temperature, so you divert blood to the skin, and sweating is actually something different now that I think about it. But what does it do when you increase blood flow to the skin? You're able to release that heat from the blood vessels. So it's a way you release heat. Danielle, what's another place that things are changing?
The kidneys and the abdomen, there's a lot less in that area.
So just pick one.
Kidneys.
All right, the kidneys. So we have 1,100 milliliters going there in the kidneys, and we half that pretty much during exercise. And what's that about?
You mainly use your kidneys for the rest and digest, and since you're doing the exercising, your body really doesn't need to run blood through those areas.
Yeah, it's about priorities. Okay, and when you're exercising, your priorities go to the skeletal muscles and these other places. All of a sudden, filtering the blood and making urine isn't as big of a priority. So we divert blood away from the kidneys to other places in the body. And then Akari, what's another place that is going on here? Yeah, so what's going on with that? It's the exact same thing. Okay, when you're exercising, all of a sudden now your digestion isn't as important. Which is interesting when you think about it, eating a meal and stuff. It goes seconds in the mouth, seconds in the esophagus, then it sits in the stomach for 2 hours, maybe 3 or 4. Then it goes into the small intestine, and that's where absorption occurs. So, if you... So we'll say absorption occurs like after 3 hours after a meal. So if you exercise 3 hours after a meal, you're actually diverting blood away from that digestive process, and that absorption isn't going to be as efficient. Priorities. And how does the body accomplish this? How are we able to divert blood from one place to the other? Ian.
That's the vasoconstriction.
That's the vasoconstriction and vasodilation. Specifically, we can vasoconstrict to the abdomen while we vasodilate to the skeletal muscles. So we can choose, the body chooses where that vasoconstriction and dilation occurs.
So isn't a lot of vasodilation happens because of histamine? Or is that?
Maybe so, that may be a side effect of histamine in inflammation, I'm not sure.
And in my micro class, that's what we were talking about.
That makes sense.
Does it, when you're exercising, are you releasing a lot of histamine then?
I don't think so, but back on that point, histamine is part of the inflammatory response, right? Which is part of the immune system reaction. So when you're fighting an infection right there, you want to vasodilate to it because
Your white blood cells can release.
and also you're creating more heat as well. And heat is part of the inflammatory response.
You're also releasing cortisol as well when you're exercising in a way that's causing stress, a little bit of stress.
I wouldn't be surprised if cortisol is released because cortisol acts on the liver and frees up glucose. It converts glycogen to glucose. This is another way to look at the same thing. This is cardiac output at rest, 5 liters per minute. This is during heavy exercise, 25 milliliters per minute. And then this just says where the different percentages of these places go. So during heavy exercise, 80% of the blood cardiac outputs go into skeletal muscles, whereas during rest and digest, 20 to 25 is going to the abdomen. All right. A few slides here.
Yeah.
What's that?
Aerobic exercise results in activation of histamine 1 and 2 receptors within the previously exercised muscle, triggering vasodilation and broad-range response. Another broad-range response.
Okay, so we want to increase cardiac output, and that's what this is all about. Increasing cardiac output. This is the net effect that we want to get to. And there's 2 ways to increase cardiac output. We can increase heart rate, or we can increase stroke volume. So these are the different ways that we increase heart rate and stroke volume. And let's just take a look at this here. But during exercise, fright, anxiety, during the fight or flight response, which of these 2 systems, the sympathetic or parasympathetic, is going to be activated? Okay, we're going with the sympathetic nervous system. And the sympathetic nervous system, these are those in the green here. Look where they synapse with. Where's this sympathetic nerve fiber synapsing on? On the SA node. Okay? Cause it to excite more quickly. So that's how we increase heart rate there. Okay. So something else I want to point out here is that you see these other sympathetic fibers going down here to the ventricles. And what those are doing is they're going in the ventricular myocardium. So when these sympathetic nerve fibers synapse, they cause the cardiac muscle cells to contract more forcefully. Okay, that's what they're doing. That's called, you're increasing contractility. When the ventricles contract more forcefully, you're increasing contractility. And this shows that the sympathetic nerve fibers are doing that. Also part of the sympathetic nervous system, we have the adrenal gland. The sympathetic nerve fiber acts on the adrenal gland, and we release epinephrine in response to that. So now epinephrine is going through the blood. And that also acts on the heart cells and increases that contractility as well. And when we increase contractility, we're shooting more blood out of the heart, so we lower the end systolic volume there. Increased stroke volume. So on this, also on this increased stroke volume, exercise increases the amount of venous blood that returns to the heart. We have these one-way valves and skeletal muscle pumps that pump more venous blood back to the heart. And what that does is it increases the end diastolic volume, and it increases the amount of blood that's going back to the ventricles. And if we do that, then we're able to eject more out as well. We increase our stroke volume. And just one point that I want to make on that, you know, our resting heart rate may be, I don't know, 70, what did we say, about 70, 75 beats per minute. But endurance athletes, like serious endurance athletes, their resting heart rate can be as low as 40 beats per minute. So ours are, you know, theirs is. Okay. Anybody know why that's the case?
It's because of exercise that increase their stroke volume, or their, like,
That's what it
the
is.
strength of their heart contraction.
So the heart muscles of these endurance athletes is a lot stronger. So what that means is that with each contraction of the ventricles, they're shooting out a lot more blood than you and I are shooting out, because it's just stronger, their heart's stronger. So they're shooting out more blood with each heartbeat. And if you're able to do that, you know, that's great. What does that mean? It means you can drop your heart rate down. Okay. Our cardiac output is the same as endurance athletes, but since their heartbeats are more efficient, they're able to do the same job with less heartbeats, basically.